In the southeast of China, one of the most audacious construction projects ever undertaken has just been completed, linking the two banks of the estuary to the northwest of Hong Kong by means of a 24-kilometer artificial sea crossing comprising bridges, artificial islands, and a 6.8-kilometer-long immersed tunnel.
There are lots of challenges in the project, many bold decisions, and it is so iconic. It has become a landmark.
Begun in 2017 and completed in June 2024, the construction of the Shenzhen Link is an engineering challenge that pushes all known boundaries in this field.
The unprecedented bridge width of 1,666 meters anticipates the development of maritime transport. We're offering a very wide navigation channel and a height that will allow the passage of container ships of the future.
This titanic project has given this prosperous Chinese region an 8-lane highway, cutting travel time across the delta to 30 minutes, whereas in the past, it took 2 hours to drive around it.
What impresses me most about this project is that despite the cost it may represent, there's a structural unity from one end of the project to the other that is spectacular, magnificent, and successful.
Original and exceptional designs, a quest for performance and durability, perilous transportation and assembly in a hostile environment, the construction of the Shenzhen Link has proven the skills of its builders, notching up world records in this engineering sector.
So we take one of the longest immersed tunnel, one of the longest suspension bridges, and we combine that into a massive project that in itself makes it a huge challenge.
For this project, the Chinese have continued to innovate, building new types of tugboats and floating cranes, coming up with designs and materials that are even more resistant to the vagaries of the weather, and building revolutionary, fully automated factories.
Really, the boundaries of technology have been pushed. The high degree of automation and prefabrication, I think, will also set new standards.
It is time to get on board for a spectacular story. The story of an incredible construction journey that has reshaped the landscape and the brilliant future of the Greater Bay Area and brought sea link construction into a new era. The South China Sea is a large corridor through which a large part of the world's maritime trade passes. To the northwest of Hong Kong, the region bordering the Pearl River estuary has become one of the most dynamic areas in China. Most of the cutting-edge industries are grouped there, and their annual economic output is close to 1,800 billion euros, 20 times the turnover of the Silicon Valley in America. This area, known as the Guangdong-Hong Kong-Macau Greater Bay Area, has more than 80 million inhabitants and already has an extraordinary transport network made up of 4,900 kilometers of highway and 2,500 kilometers of railways, a combined distance that would connect Paris to Beijing. Added to this are 5 international airports and 3 of the largest commercial ports in the world. However, demand continues to grow for road infrastructure to enable faster crossing from one bank to the other. This is how, in 2017, a new crazy project was initiated, connecting the cities of Shenzhen and Zhongshan by spanning the estuary using a bridge and an underwater tunnel in order to reduce the travel time between these two constantly developing cities. Thanks to this new maritime link, the journey will be 4 times faster than going around the bay by the north.
Such a project, of course, can only be justified by very strong socio-economic reasons, and it was certainly supported by a strong political will to build an exceptional structure.
When the link will be opened, road traffic will exceed 100,000 vehicles per day. It will be two-way and on 8 traffic lanes, which makes it one of the most ambitious challenges of all trans-maritime projects in the world.
But I think in terms of ambition, it was really the time frame to construct a link of that scale, 24 kilometers, within the given time frame of 7-8 years. That's a big challenge.
And building such an edifice in an aerial and aquatic environment in perpetual motion was another major challenge. From the very beginning of the project, the specialists therefore focused on analyzing and understanding the natural elements present in the estuary, the hydrometry, the river and sea currents, and of course, the winds.
The typhoon winds is a major issue in these areas, so we do quite extensive testing of the structure. We build actually a model, and then we expose this to different wind and different directions to make sure that it's stable under these severe conditions.
These wind tunnel tests reproduce the typhoons that regularly pass through the Greater Bay Area. The engineers therefore test several designs and found out which is most appropriate.
It's about to form the structure in a way that the wind can flow around the structure to make as little resistance as possible.
And we can see here that for the structure of the suspension bridge, the section was fitted with a fairly pointed nose, which is quite rare in this type of structure, and which, like an airplane wing, will allow the air to flow around the structure as smoothly as possible.
This tapered shape has significantly optimized the aerodynamics of the bridge, allowing it to withstand typhoons with winds exceeding 300 kilometers per hour. The other major challenge was the design of the submerged elements, because the Lingding-Yang, the central channel of the estuary, has a weak ocean current. The installation of a bridge tunnel over its entire width should therefore, under no circumstances, reduce this current further, at the risk of seeing sediment deposits accumulate and hindering its natural functioning. Its S-shaped design is therefore not a coincidence.
The reason for the winding route is mainly due to the need to design the bridge perpendicular to the water flow, which is more conducive to flood control and tidal regulation.
By imagining the route of the bridge perpendicular to the direction of water flow, the obstruction generated by the bridge piers and artificial islands can be considerably minimized. And to further reduce this impact, thought has also been given to the design and shape of these elements. To do this, Chinese engineers designed a scale model of the estuary, reconstructing the relief and currents of the Pearl River estuary over 100,000 square meters. For 2 years using models, the engineers were able to carry out hundreds of experiments like this one.
This little piece of plastic is a tracer particle. We're using 40,000 of them in this experiment, and above me are 282 cameras that allow us to follow the trajectory and movement of the particles, and to study the hydrodynamic impact of the Shenzhen Bridge on the Lingding Channel.
These multiple experiments have helped to optimize the design of the bridge piers and the 137,000 square meter artificial island planned to be built right in the middle of the estuary.
It was very much about coming up with shapes that are streamlined so that will naturally have as little blockage as possible. And then you would also notice that in certain parts of the structure, there's only one pier. So even though there are two girders, they're resting on one pier instead of having two pier shafts. And that also helps to limit the water blockage.
For the West Artificial Island, which will be the entrance to the underwater tunnel, a diamond shape with curved edges was chosen. This design transforms the ocean into a sky, in which an elegant kite is floating, pointing east towards the rising sun.
The concept of a kite attached to a string, rising towards the sun and chasing the light is like a poem or a painting, imbued with a great sense of harmony. This concept embodies what we believe to be an elegant masterpiece of engineering.
Kite, it's linked to Chinese culture, but it's also, I think, a toy that a lot of people are familiar with. So in a way, it's also a universal language.
There was a lot of effort put into the fact that it had to be one flow, even though it was an island, a bridge, and a tunnel. So it's more than just a transport element, but also an aesthetic pleasing element in the context where it's placed.
The first works in the estuary began in May 2017. The countdown had begun because the Chinese engineers set themselves the goal of completing this 24-kilometer maritime link in just 7 years.
7 years to construct a link of this scale is certainly ambitious and a huge challenge.
But on the other hand, Chinese are very good at implementing at speeds.
Within less than 2,500 days, they will have to build a cable-stayed bridge, simple bridges called approach bridges, a suspension bridge, 2 artificial islands, and an underwater tunnel almost 7 kilometers long due to the proximity of Shenzhen International Airport, whose intense air traffic prohibits the construction of any high buildings. A titanic challenge that must also combine lightness and long-lasting performance.
Lightness and durability are not incompatible. They are even complementary, as long as you choose the right materials in the right place.
One of the approach bridges, located between the cable-stayed bridge and the suspension bridge, is 13 kilometers long. It is supported by more than 120 concrete piers, firmly anchored in the estuary and spaced as far apart as possible so as not to obstruct the current. As a result, the engineers had to design long deck spans that were both rigid and lightweight. And to do this, they had to use the most suitable material, steel. In just 2 years, nearly 100,000 tons of steel box girders were manufactured in this ultra-modern factory built specifically for the project. From cutting the plates to welding, everything is automated.
I think you can rely on a much better quality with an automated process, and you can also obtain speed and repetitiveness to a higher degree.
The box girders, which will have to support the weight of the cars, attain their rigidity thanks to the U-shaped metal reinforcements. However, the structure remains very open, which keeps it light. For this project, the assembly method was enhanced with a technological innovation consisting of welding these reinforcements from the inside in a space barely larger than a volleyball, a world first made possible thanks to this new robot.
Traditionally, it has only been possible to weld from the outside, so as you can imagine, it leaves the potential for a little gap on the inside. It will ultimately mean that the material will break in fatigue, as we call it. By welding from the inside, that quality of that little detail is actually improved quite a lot. So this technology is definitely an innovation and a leap forward that we will take a lot of inspiration in other projects.
Once assembled, each box girder is more than 100 meters long and weighs 1,500 tons. But once it leaves the factory, how can this imposing structure be transported? And how will it be hoisted onto the bridge piers right in the middle of the estuary? The answer is called Sky One, a crane ship 84 meters high with the largest lifting capacity in Asia, because it can lift up to 3,600 tons, the weight of 80 semi-trailers.
Sky One should cross the Lingdingyang Canal in 20 minutes. I'll report back to you.
Okay, understood.
The Sky One is a ship that can both transport elements weighing several thousand tons and put them in place without any problem, with the required precision.
In record time, this floating forklift reaches the steel box girder's final location. The pilots have to demonstrate great dexterity as they approach the bridge.
If the wind and the current are going in the same direction, the ship is in great danger. It could very easily drift out of the canal and hit the bridge. Now that all the piers and the first decks have been installed, any collision would be extremely dangerous.
The Sky One can lift the box girder up smoothly to about 60 meters. The problem is that at this point, the bridge deck peaks at 61 meters above sea level. To successfully complete this assembly, the engineers are counting on their most formidable enemy, which then becomes their best ally, the tide.
In the middle and at the beginning of each month, we will take advantage of the maximum tide level to install the highest girders.
At high tide, the Sky One goes into action. Despite the wind and waves that disrupt the maneuver, the box girder comes to rest, slowly but surely, on the bridge piers. It will then be welded to the previous elements. In less than 2 years, this crane ship will have completed the assembly of all the box girders of the main approach bridge of the Shenzhen Link. An amazing feat of efficiency and speed.
Generally speaking, planning is very important for builders around the world. As far as the Chinese are concerned, it's certain that there's a question of honor on top of it all.
Everything is excessive in this cross-sea highway project. The Shenzhen Zhongshan suspension bridge is a perfect example. It is planned to be the highest in the world, reaching 76.5 meters above the water, the equivalent of a 26-story building or 2 ocean liners like the Titanic stacked on top of each other. The bridge will also be the world's largest span steel box girder suspension bridge in the sea, measuring 1,666 meters long. But these extraordinary dimensions are not just the whims of an engineer. The Shenzhen Link is located in one of the busiest areas for global maritime trade and is designed to last a minimum of 100 years.
In view of the development of maritime transport, with a width of 1,666 meters, we offer a very wide navigation channel. And why did we choose this height under the deck? Because we studied the trend of ship development over the next 50 years, and we've planned enough clearance heights to allow the container ships of the future to pass through.
To achieve this amount of clearance under the suspension bridge, the main towers that support the cables must be 270 meters high. A new challenge for the builders, who have once again custom-developed a construction machine capable of achieving this feat. Directly installed on-site, this circular micro-factory built the towers, floor after floor, rising with them throughout the process. For each tower, 48 operations were enough to pour 50,000 cubic meters of concrete onto 7,400 tons of prefabricated steel reinforcements. This is how the 270-meter towers were completed in barely a year of work. At the same time, 580 meters from each of the towers, 2 underwater anchors made of reinforced concrete were built to accommodate the ends of the 2 cables that will support the load of the bridge.
In this case, they weigh 1 million tons, and that doesn't surprise me at all, since they have to withstand this phenomenal force generated by the cable. These are real buildings. In fact, they're the most important buildings in the bridge. Without the anchor blocks, there's no suspension bridge.
Even before the weight of the vehicles is added, the body of the suspension bridge alone will weigh 85,000 tons, a load that these colossal anchors, the largest in the world, can easily support. But the cables themselves must be able to withstand such tension. And while the word cable is quite simply used, it's actually a much more complex assembly.
The basic element is a 6mm diameter steel wire that is then combined into what we call a strand. And a number of these strand cables then make up the entire cable that is then compacted and made into a round cable.
The entire success of the project, therefore, lies in the design of the 25,000 steel wires that make up each cable, and which is the result of 3 years of research and development. To make ultra-strong steel wire, workers perform 9 successive cold drawing operations, a passage through a series of presses and gears that stretch the wire and reduce its diameter from 13 millimeters to just 6 millimeters at the end of the line. And as surprising as it may seem, a wire that has been reduced in this way will be much stronger than the original larger wire. This is because the stretching has reorganized the steel crystals inside the wire into a much stronger assembly.
It's hard to explain, but it's a fact. When you pull on steel and torture it, well, it becomes better.
By carrying out laboratory tests in an atmosphere typical of that of the estuary, the engineers very quickly realized that this steel wire, although reinforced by cold drawing, wouldn't quite meet the durability requirements of this extraordinary project because the coating traditionally used, an alloy of zinc and aluminium, is sensitive to corrosion.
The location of the Shenzhen Link is a very harsh environment. It's hot, it's humid, there's a lot of salinity in the air. So therefore, there was a lot of focus on the coating on the individual steel wires and testing to make sure that it could actually live up to the requirements.
To prevent the steel wire from rusting too quickly, the engineers enhanced the zinc-aluminium coating with magnesium, a metal that's more resistant to corrosion. This technological innovation increases the durability of the steel wires by 50%, an added guarantee to ensure that the cable will last at least a century in the harsh environment of the Pearl River estuary. Coated with their zinc-aluminium-magnesium alloy, the steel wires are then assembled in the factory to form strands. Rolled up into 3-kilometer-long coils, they are transported to the construction site, then rolled out from one end of the suspension bridge to the other, and anchored independently of each other in the pulling chambers of the anchor blocks.
So the breaking of one strand would have no impact on the strength of the structure, but I don't think it'll ever happen.
This is how, starting with a simple 6mm diameter steel wire placed in the center of a 127-wire strand, a main cable composed of 199 strands is formed. With a total diameter of 1 meter, each of the bridge's 2 cables will be able to support a load of 150,000 tons, the equivalent of the weight of 5,000 humpback whales. Their first mission will be to help position the steel box girders that will form the deck of the suspension bridge. A crane has been installed astride the 2 cables of the bridge, and the very first girder is about to be put into place 91 meters above sea level.
Checking complete. Start hoisting.
Okay.
3, 2, 1, lift.
The section is now starting to take off.
Each box girder is about 10 meters wide and weighs 226 tons, the weight of 150 cars. Despite some wobbling, the very first section of the bridge is slowly making its way to its location.
The girders are hoisted from barges up to the final position, and then they are connected by means of hangers. So a vertical element that connects the main cable to the girder.
In the space of a few months, more than 200 beams will be suspended from the 2 main cables, then welded together.
The state of the art is that we have a fully welded box girder from one end to the other end, as from anchor block to anchor block. So it's actually fully continuous over more than 2.5 kilometers in this case.
All the other sections of the Maritime Link were also welded together or connected by expansion joints, forming a continuous and uniform track 17 kilometers long. A future 8-lane highway with a total surface area of 380,000 square meters that has been covered with a very specific surfacing. An asphalt enriched with epoxy, a waterproofing resin that will protect the metal structure of the bridge while guaranteeing great driving comfort for the 100,000 users expected each day. Their comfort and safety are obviously a priority. From this point of view, artificial light will also play a predominant role at nightfall. Because although the primary intention of the lighting is to aesthetically highlight the contours of the structural elements of this cable-stayed bridge, its floodlights should not, under any circumstances, interfere with driving. An initial lighting system, deemed too dazzling, was dismantled only a few days after its installation. But today, the teams are putting things right.
We've now changed for lighting in an upwards direction. The lights are installed on the side of the guardrail, creating a light curtain from bottom to top that effectively avoids the glare problem for drivers. The installation is complete, and we will now be able to discover the final effect.
For the very first time, the cable-stayed bridge is standing out in the night. And with it, the entire Maritime Link is illuminated. All the elements come together to form one unique link, a resplendent 17-kilometer structure that seems to float above the water and majestically meanders through the estuary. At its end, the artificial island mysteriously interrupts this luminous furrow. Sparkling, this kite is the gateway to what is undoubtedly the most impressive and complex architectural feat of this cross-sea link. An 8-lane, 6.8-kilometer-long underwater tunnel that leads to the eastern shore of the Great Bay. To understand how such a structure came to life, we need to go back 7 years.
The Zhongshan Link connects Zhongshan on the west side with Shenzhen on the east side. And the point where the link connects to land on the Shenzhen side is very close to the airport. And therefore there were quite strict height restrictions on the structures at that location. And therefore the tunnel is the logical response to that constraint.
At the same time, the shipping channel has been completely freed up. There's no pier, there's no bridge, there's no risk of a boat hitting something, and that's also very important.
2 islands were designed by the architects to accommodate the entrances and exits of this underwater highway. The artificial island in the west, which will also house the tunnel's ventilation infrastructure and its control center, is the first structure to have been built.
And then, of course, the construction challenges is that you have to construct an island on this estuary mud that is there, and this is a difficult thing to work with.
Moreover, building a stable island in a constantly moving aquatic environment is a structural challenge. To achieve this, the engineers chose what's known as the coffer dam technique.
For the artificial island, we're starting from scratch. We're building an enclosure that we can drain, and in which we can work as if we were on dry land. This artificial enclosure is, in this case, made up of metal tubes driven into the ground against each other.
At the start of the work, in May 2017, the goal was to waste as little time as possible so as not to hold up navigation in the estuary for too long. So the larger the cylinders, the fewer will be needed to form the base of the island. The manufacturing plant started working on 57 cylinders with a diameter of 28 meters and a weight of 650 tons. A new world record for these construction elements.
The main problem with the large diameter cylinders used here is that they have to be driven into the ground. So you need to have metal tubes that are strong enough. But it's a good technique because it's ultimately part of the final structure that will withstand the sea, the effects of the swell, and many other things.
To drive the cylinders into the ground, an imposing system of hydraulic vibrating hammers was used to sink the tubes, exerting a pressure of 6,000 tons on them. But there's a problem. The seabed has particularly hard intermediate layers at this precise location. Forcibly driving in the cylinder could lead to multiple deformations and a very unstable installation of the structure. The technique, therefore, requires further adaptation.
This is one of our characteristics, us Chinese. We are constantly adapting and developing our techniques based on what already exists. Now, wherever steel cylinders need to be driven, whether the ground is hard or soft, our new process guarantees success.
The innovation is a method called penetration assisted by deep soil mixing. Drills are used to upstream of the cylinder installation. They will help transform all these diverse layers, hard and soft, into a sort of plasticine clay with a relatively uniform consistency. This homogeneous seabed will thus be able to accommodate the cylinder and ensure that it is firm and perfectly straight. Thanks to this method and the limited number of cylinders, it only took 4.5 months to complete the enclosure structure. Once the central part was filled, the island had a solid base of 137,000 square meters, the surface area of 19 football fields. 4 years later, the sand has given way to concrete and the first amenities, while nearby, underwater, the future underwater tunnel's outline has begun to take shape.
Before installing an immersed tunnel, it is necessary to dig out or to excavate a trench. And then a gravel bed will be placed at the bottom of the trench. And this is because it needs a very even support so that there are no undesirable bending effects or stresses at one corner of the tunnel element.
This tunnel bed will have to be 5 kilometers long and 330 meters wide. To excavate this deep water trench, 300,000 cubic meters of rock will have to be moved. As long as the rock is very friable, decomposed granite, everything is fine. But often, the digging teams are stopped dead in their tracks.
We've hit an area of the northern trench where we can't dig any further.
What is the exact location according to the measurements?
There, between 30 and 40 meters, there's a 3-meter gap. We'll have to move on to the rock drilling process.
This type of drilling is usually done by blasting, a technique that the engineers immediately ruled out in this case. For a simple reason, the Lingding Channel is a migration route for Chinese white dolphins, an endemic species that could be endangered by underwater explosions. The most recalcitrant rocks will therefore be drilled using a 35-ton rock hammer submerged in free fall at a speed of 20 meters per second.
To process 1 square meter of rock, it would probably have taken 4 kilos of explosives. With this rock drilling process, it only takes 2 to 3 hammer operations for the same area.
More than 4 years of work and thousands of rock drilling operations like this one were necessary to prepare the tunnel bed. A bed on which a perfectly even mattress must now be laid, upon which the 32 tunnel sections will be safely placed. This is where the Jinping No. 2, the world's largest gravel leveling vessel, comes into play.
The Jinping No. 2 is effectively a floating factory, which allows you to get into the right position at sea, to work at great depth in a fixed and stable manner, since the forelegs are telescopic and can be adjusted to a seabed that could have any shape. And it allows the part of the ship that is floating to be lifted and to become independent.
Firmly anchored and isolated from the wind, currents, and tides, the ship can thus work in complete stability. For each of the 32 tunnel sections, this underwater 3D printer will fill the trench with 10,000 cubic meters of gravel, the equivalent of 4 Olympic swimming pools. The gravel is projected towards the bottom at a frantic rate of 800 cubic meters per hour, then leveled by compaction.
This barge is a concentrate of technology, in the sense that it's equipped with a trolley that moves a dipping tube that's set to the desired altitude by laser, which deposits the gravel in strips that will serve as a receiving mattress for the tunnel elements to be laid.
The leveling is carried out with such regularity that the deviations in height never exceed 4 centimeters. A precision that guarantees that the tunnel will be assembled on a perfectly flat base. Thanks to this technological monster, it took less than 130 days of work to prepare the 5 kilometers of trench. The mattress is therefore ready to receive the sections of the future underwater highway. A few kilometers away from the construction site, the largest robotic factory in the world was built with the sole mission of manufacturing the 32 tunnel sections because the technique chosen is quite unusual. It will combine concrete commonly used for this type of structure with steel. And the reason for this is the exceptional width of the tunnel, 46 meters, a world first.
The link carries 8 traffic lanes, 4 in each direction. That is quite a lot, and for an immersed tunnel, it is pushing the boundaries. And if something special is not done, then the top slab would deflect. So it was ultimately decided that the concrete steel sandwich solution was the best answer to the challenges.
Indeed, the wider the tunnel becomes, the more its weight and bearing surface increase. It then becomes more fragile and risks distortion under the weight and pressure of the water. To avoid deformation of the structure and attain better rigidity, the engineers chose to use steel plates, at least 40 millimeters thick, on the internal and external faces of the shell, which they will then fill with concrete. Once assembled, each section is 165 meters long and 46 meters wide, with a surface area of 7,600 square meters, equivalent to 18 basketball courts. As tall as a 3-story building, it measures 10.60 meters, and its shell is made of more than 10,000 tons of steel. But there's a problem. The marine environment represents a worrying threat for a metal structure like this, because seawater, rich in salt and oxygen, is very corrosive. The engineers had to adapt once again to this constraint.
In order to avoid corrosion of the element you don't want to corrode, you put what we call a sacrificial anode in. So when the corrosion happens, it happens on your sacrificial anode rather than on the structure you have put in the water.
Each tunnel section is thus protected by 552 of these metal blocks, welded to the structure, whose role is to attract corrosion before it damages the tunnel walls. For this project, the Chinese engineers chose to manufacture these elements with an aluminum alloy that increases their lifespan by 50% compared to previous models. Enough to protect the tunnel for a long time. In total, 20,000 of these sacrificial anodes will be produced to cover the 5.5 kilometers of the submerged structure. Equipped in this way, a section weighs around 12,000 tons. However, it is far from having reached its final weight, because at this stage, the metal structure is in reality only an empty shell and potentially deformable. Before being submerged, it must therefore be filled with a very specific concrete.
I think the main problem is to avoid air entrapment in corners inside, to make sure that the whole volume is filled with concrete.
Because it's basically an area that nobody will be able to inspect afterwards.
A section has 2,255 compartments to fill. As soon as the concrete is poured, the result is irreversible.
There is no room for error, because if the concrete is too thick or too quick to solidify, some compartments may not be filled correctly, weakening the entire structure.
And there were really a lot of tests carried out to come up with the right recipe, the right mix for the concrete, because it has to flow easily to fill all the voids. Of course, it also needs to be capable of developing the necessary strength. And then it has to be self-compacting.
More than 1 million cubic meters of concrete will be required to meet the needs of the 32 sections and 5.5 kilometers of submerged tunnel. Injecting the mixture manually is obviously out of the question, especially since to avoid premature solidification, the concrete must be poured within 90 minutes of leaving the mixing station. A new race against time begins, and once again, a robot will take up the challenge.
What was impressive is that this concrete filling was done using a machine specially designed for this purpose, which looks like a giant spider, and has the remarkable property of being able to detect the compartments to be injected, and at the same time, the ability to fill them and check that they are properly filled at the end of each operation.
Autonomously following the itineraries programmed by the engineers, the machine worked tirelessly for almost 3 years to fill the 32 tunnel sections with concrete in an extremely regular fashion. When they leave the factory, each section weighs 80,000 tons, a colossal amount that would be extremely difficult to move by land. The engineer's strategy consists of using the estuary as a load-bearing element, because once temporarily closed at both ends, no matter their weight, these sections will float.
Thanks to Archimedes, good old Archimedes. So Archimedes states that a body immersed in water receives a thrust from this liquid in an upwards direction equal to the weight of the volume displaced. In short, Archimedes really means that the thrust of the water carries the load.
To tow these heavy sections more than 50 kilometers away from the factory and safely across the Pearl River estuary, the Chinese engineers once again had to design a custom-made tool. The result was this super-equipped vessel, the first in the world to allow transport by flotation and the installation of immersed tunnel sections designed and manufactured by the project's engineers in just 3 years. Equipped with 2 main engines, 8 high-power lateral thrusters, and 158 real-time positioning sensors, this super-sized vessel is capable of towing the 80,000 tons of the immersed tube against wind and tide without deviating.
Once again, the barge used to install the tunnel sections is a 2-in-1 device, if I can call it that, in that it allows the elements to be transported while keeping them as stable as possible, and at the same time to be placed gradually with the desired precision on the seabed.
Once on site, positioned above the tunnel trench, the section has to be sunk as quickly as possible. Because in the Lingding Channel, the weather and hydrographic conditions can change very quickly. This time, the immersion will take place at night.
To all departments, descend over 5 meters at a speed of 0.3 meters a minute.
In the darkness of the night, Section E14 begins its descent towards the tunnel bed 40 meters below the ship. At this depth, it will have to be placed next to the previous section without hitting it. The operator's concentration is at its peak.
It's a challenging task because everything takes place in the current, in water with limited visibility. It is extremely critical for the performance of the tunnel that each segment is installed within the given tolerances, because this is how it gets its water tightness, its performance, and long-term durability.
The section is now less than 1 meter away from the seabed, but at this precise moment, the monitors go crazy. The sea currents are getting stronger and stronger, and the structure is feeling the effects.
The section shook violently, with a range of shaking and oscillation that reached 0.6 meters. If it is shaken again, it risks colliding with the section in front of it and damaging the most precious element, the seal, which would render this section unusable.
The ship's captain and the engineer in charge of operations guide the operators to use the traction and reaction force of the cables to stabilize the section, balance it, and prevent any further oscillation.
Winch 1256, and again the 1278.
By releasing and retracting the cables, centimeter by centimeter, the 5 operators managed to keep the section stable enough for it to land on the tunnel bed in the right position, and only 5 centimeters away from the previous section. This agonizing descent of only 80 centimeters will have taken more than an hour.
I was anxious and sleepy, but there was no other way. This work must be done step by step. Slow work produces meticulous work.
At this point, the docking of the 2 sections is almost a formality. Thanks to a system of hydraulic jacks, tunnel section E13 finishes drawing in section E14, which this time joins with an offset of only 0.8 millimeters, giving the team a new record for precision. In the following year, all of the tunnel sections are submerged and joined without difficulty. All except one. In June 2023, 167 meters of the section are still missing at the center of the future underwater highway. Section E23 is the last portion of the tunnel. It is also the one that integrates the final joint that will connect it to section E24, sealing the entire structure. This final component is a world first, because until now, underwater tunnels have been completed with an independent joint, separate from the other sections.
Here, the final joint is integrated into the last tunnel section, hidden inside the 165 meters like a drawer. Once the E23 section is in place, it will be pushed out.
There can be no errors in the deployment of this final joint, at the risk of jeopardizing the water tightness of the tunnel. But it's a big challenge, because when the section is submerged at depth, it will be subjected to huge pressure from the seawater and resistance that will have to be overcome in order for the impressive 1,600-ton joint to be pushed out of the section. The designers have therefore opted for an ingenious double push process. The first is exerted by hydraulic jacks, while the second is a push by water pressure. Inspired by the operation of a syringe to suck up liquid, the space located behind the final joint is connected to the sea. The injection of water inside the seal will thus compensate for the pressure exerted by the sea on the outside. Thanks to this technological innovation, 8 jacks will be enough to bring the final joint out of its hiding place. At this stage, the process is only a theory. It remains to be seen if, on D-Day, everything goes to plan. On June the 9th, 2023, the transport and installation vessel begins its final crossing of the bay, towing the centerpiece of the Shenzhen Link. On board, the young engineer in charge of installing section E23 knows that the stakes are high, because this time, he has to place the last piece of the puzzle between 2 previously installed sections.
The excess width on both sides is less than 80 centimeters, so we will be operating in a very narrow space. At the slightest abnormal underwater movement, the section will collide with the adjacent tunnel sections.
With their previous experience, the operators have acquired a particularly high level of coordination. Under the nevertheless worried gaze of their supervisors, they carry out this last descent with excellent control, placing the section on the tunnel bed with remarkable precision. However, the team isn't claiming victory yet. Tomorrow, they have one last operation to complete, deploying and securing the final joint. If this step is completed successfully, these men will form part of the history of underwater tunnel construction. Their technological innovation is now taking its final test.
First push distance of 3 centimeters. Push speed of 5 millimeters per minute. Start.
At a depth of 27 meters, divers carefully monitor the proper deployment of the joint. Their mission, to alert the surface personnel to the slightest incident. And from the first pushes, they report a worrying phenomenon. A bulge seems to be forming at the top of the final joint.
Check the damaged area and determine its exact position.
The operation is immediately stopped. The engineers hold their breath and analyze the situation in depth.
Since there's still air inside, the joint sometimes swells during the thrust. We finally understood that it's rather a good thing, because if it swells, it means that it's well sealed against air and water. No problem, we just need to regulate the thrust speed well.
Resume a synchronous thrust of 13 centimeters.
When the joint is only 50 centimeters from section E24, the engineers carry out additional monitoring with an all-new measurement and control system. A binocular camera connected by a cable to the final joint. In real time, it provides the operators with remarkably precise docking data. Centimeter by centimeter, the builders' efforts are about to be rewarded. And after 13 hours of tension and painstaking work, the gamble pays off.
I'm happy to announce that the final operation has been successfully completed and that the Shenzhen Link tunnel is now fully connected. Thank you all.
It was a great relief for the Chinese engineers, and at the same time, a source of pride. They invented something, they innovated, they succeeded. And I think it's an innovation that will be used again in the construction of this type of immersed tunnel.
7 years after the beginning of construction, 17 kilometers of bridges and nearly 7 kilometers of immersed tunnel have been connected, without the construction site being delayed by a single day. Innovation after innovation, record after record, this titanic project was an incredible technological and human adventure, making the dream of 15,000 builders come true.
Due to the scale of the Shenzhen Link, there have been a lot of innovations, and really the boundaries of technology have been pushed. New tools have been developed specialized to specific tasks. The high degree of automation and prefabrication, I think, will also set new standards.
And that will go into the catalog of solutions that will be applied for future projects. I'm absolutely sure about that.
On June 30th, 2024, the 24-kilometer Zhongshan Link was open to traffic. As planned, this trans-maritime highway is exceptionally wide, with 8 lanes upon which vehicles can travel at speeds of up to 100 kilometers an hour. It connects the city of Zhongshan to the city of Shenzhen in less than 30 minutes compared to 2 hours previously. And beyond its functional aspect, its elegant silhouette transforms this crossing into a real journey, a moment suspended in time.
The Shenzhen Link has already become a landmark for the region, and it makes me feel incredibly humble and proud of having been just a small part of it. We engineers, and we spend a lot of time calculating and making drawings and analysis, but really the big reward is seeing our structure constructed and really coming to life.
The daily use of this infrastructure by more than 100,000 vehicles will undoubtedly bring a new dynamic to the region's road network. On the seaside, prototypes of the container ships of the future are already passing easily under the world's highest maritime suspension bridge. Here, in order to pursue and intensify the economic and social development of the Greater Bay Area, the Chinese will have invested the equivalent of 5.7 billion euros, and above all, an impressive amount of sweat.
All major projects impress the world, but it has to be an opportunity, and in no case an unjustified desire to play to the gallery, as the saying goes. Here, there was a real need. They've built a remarkable and magnificent structure, and I believe they can be proud of it.
Much more than a simple highway, the Shenzhen Maritime Link is a dazzling and a harmonious testimony to the ambition that brings people together. Its construction will leave its mark on the history of offshore construction, revealing the expertise of Chinese engineers and builders, and their constant capacity to adapt to the constraints and the excesses of the projects they have dreamed up.